Let's go ahead and start talking about the ground state and the excited state. It says, how can you represent an excited state atom in nuclear symbol notation? So let's just take hydrogen, for instance. To represent an excited state, we can just draw a star beside it, or my representation of what a star looks like. Number two, it says, what happens to move an atom from a ground state to an excited state? All it takes is just an element or an electron absorbing energy and jumping energy levels up to a higher state. Which of the substances below are in the excited state? Go ahead and look at one and see if you can figure three out. Looking at number four, it says draw a model of the atom below in the ground and excited state. So to do this, we can draw hydrogen. There's its nucleus, there's its first energy level, and we draw it with one electron there, and it's in its ground state. To be in the excited state, there's the nucleus, first energy level, second energy level. Draw an electron in the second energy level, and it's in the excited state. The next one is kind of jam-packed with little clues. Stable sulfur anion, and so we're dealing with sulfur, so it's going to be 16 electrons. And it's an anion, so therefore it is stable. It has gained 2 electrons, and it now has 18. So we're talking about we're going to have 3 energy levels there, and so it's all stable. So you're going to have the first energy level, second energy level, third energy level, and you're going to draw 2 electrons on the first energy level, 8 electrons on the next, and then another 8 electrons on the outer energy level. To show it in an excited state, we would just add one more energy level and put one electron on that outside edge. Looking at neon, go ahead and it has 10 electrons, and see if you can't do that one for neon. Looking at spectroscopy, it says differentiate between absorption and emission spectroscopy. An absorption spectroscopy just shows all the light except the light that was absorbed to make the electron jump an energy level. And an emission spectroscopy is just showing when that electron drops back down to the ground state, it emits light, and so therefore it shows that light. Number 6, it says describe what light is, be complete as possible. Light is both a photon, a particle of light, and it is also a wave. We call it the wave or the wave particle duality of light, that it's both those things at the same time. Number 7, it says describe below, including range, application, and function. And so we should be able to get these straight from our notes. This is just pulling straight from our notes. When we're looking at this, we're talking about radio waves. We're talking about that they have a very high wavelength, a very low energy, that they're used to transmit information. And so we can pull all of that from the notes. Go ahead and try infrared and ultraviolet. Now let's get into some of the math of this. It says solve for the unknown using the energy equation. We know the energy equation is E equals hf. So h is Planck's constant, f is frequency. So calculate the energy of a single photon. Now when we're talking about number of photons, all we have to do is just remember that there's an n there. But when we're talking about a single photon, this is just 1, and so therefore our equation is just E equals hf. If it's a number of photons, like in our next one, we'll go ahead and put a number in for n. But right now it's 1, so let's not worry about it. So our frequency is going to go here. Remember that Planck's constant is 6.63 times 10 to the negative 34th, which that would go there. Remember plugging that into the calculator. Make sure you use the function or the button for times 10. Don't try to plug it in with the caret sign and everything else. On the TI-84, it is second comma. So we would press 6.63 second comma negative 34 times our frequency, which is 5.6 times 10 to the 14th. Multiply those together and we should get 3.71 times 10 to the 19th joules. Negative 19th joules of energy. Looking at the next one, it says calculate the energy of 10,000 photons. So our equation is now E equals hf n being the number of photons, f being our frequency, h being Planck's constant. Plug that into a calculator, we should get something right around 5.24 times 10 to the negative 13th joules of energy. Go ahead and leave C for you to do. Pretty challenging problem, but I think you can handle it. Looking at number 9, it says solve for an unknown using the speed of light. So C equals C equals lambda F. There we go. And we're looking at this. It says calculate the wavelength. So we're going to, this lambda, that is wavelength. And so we're going to have an equation of wavelength equals the speed of light divided by frequency. Speed of light is a constant, 3.0 times 10 to the 8th meters per second. And then we have our frequency, which goes right there. Now remember that speed of light is in meters per second, which we'll use that here in a second. But plugging all this at the top part into the calculator, we should get 2.5 times 10 to the negative fifth, and that would be in meters. Now on the next one, it says calculate the frequency of a 580 nanometer photon. And so that's the wavelength of it. And so we're calculating frequency, which our frequency is going to equal the speed of light divided by wavelength. Remember that wavelength has to be in meters. So we go ahead and put this 580 times 10 to the negative ninth. And that'll go ahead and put it in meters for us. And then we have 3.0 times 10 to the 8th meters per second. In C, it says calculate the wavelength of a photon that much energy. So you're going to use both equations. The E equals HF, and C equals R wavelength times frequency. We can go ahead and combine those, and you can go ahead and plug that in and solve for C. Number 10, it says what does the octet mean? Octet means 8. In number 11, it says draw the Lewis dot diagram for a stable form of sulfur. If it is stable, that means that it has 8 valence electrons. So sulfur with 8 dots around it. Okay, stable form of bromine would be bromine with 8 dots around it. Stable form of oxygen, oxygen, 8 dots around it, because octet means 8 and 8 is stable. Looking at our sublevels, orbitals in the periodic table, it says label the following on the periodic table and state how many electrons can each orbital hold. So when we're looking, we have our S orbital. It can hold 2 because it has 2 columns in it. Then we have our P orbital, which can hold 6 because it has 6 columns in it. Then we have our D orbital, which can hold 10 because it has 10 columns in it, and our F orbital, which has 14 because it has 14 columns in it. Moving on to the off-Bob Pauli exclusion principle and the Hund Rule. When we're looking at these, it says define the terms below using Coulomb's law. The off-Bob principle states that we fill electrons from the lowest energy to the highest energy. When we're thinking about Coulomb's law, that those electrons are going to be attracted to the nucleus the closer that they are to it, and so therefore those protons will pull in those electrons to the lowest possible energy possible. The Hund Rule, when we're talking about the Hund Rule, we're talking about the filling each suborbital with 1 electron before it gets 2. When we're talking about the Coulomb's law, we're talking about the fact that electrons repel each other, and so therefore they are going to get as far away from each other as possible. So in different sublevels first, before they are forced to be in the same suborbital together. So looking at C, it says the Pauli exclusion principle that electrons must have different spins, and so therefore if they are in the same suborbital, they will have different spins because those opposites are pushing each other away from one another. Looking at 14, it says draw an electron energy diagram for an atom of nitrogen. So when we're looking at the electron energy diagram, we're following the off-ball rule. Nitrogen is going to have 7 electrons, so we will follow 7. So 1s is our first, and it has 1 orbital, and so therefore, or suborbital, so therefore it holds 2. And then 2s, which again, s has 1 suborbital, it can hold 2. And then 2p, which it has 3 suborbitals. We only have 3 electrons left, and so therefore each suborbital gets 1. We're going to do the same thing with oxygen, except we have 8 for oxygen. So same order, 1s, 2s, 2p, 1, 1, and 3. We go 1, 2, 3, 4, 5, 6, 7. Then we come back and put 8, and it should look like that. Go ahead and try sodium. Looking at number 15, it says write the electron configuration for the elements below. Using our periodic table and using that off-ball filling order, it's the same order. Nitrogen has 7 electrons, so follow the same order. 1s, 2. That took care of 2 electrons. We're down to 5. 2s2, that took care of 4, another 2, which is a total of 4. We're down to 3. The next in line is 2p, and then we have 2p3. And you can look, 2 plus 2 is 2 plus 2 is 4, plus 3 is 7. So for oxygen, it should be 1s2, 2s2, 2p4. 2 plus 2 is 4, plus 4 is 8, and so we have enough. Go ahead and try sodium. Looking at number 16, it says identify the element based on the information below. We have 10 protons, so therefore it is neon. We have 12 neutrons, so 12 plus 10 is 22, so it's neon 22. We'll check and see if it has a charge. That helium there is in noble gas notation. It just represents 2 electrons. So 2 plus the 2 right there is 4, plus 6 is 10. 10 protons, 10 electrons. It is neutral.